Boston Climate Institute.
So, if we are going to start, so let's introduce real data from EDF. We'll present you things about telemark software that is developed and used in EDF.
Thank you, Guy. Good morning, everybody. Okay, so maybe some part of you knows already me. So for the others, my name is Riyad Atta. So I come from ETF, which the French electricity board, with it's one of the biggest electricity producer in the world. So we are more than 160,000 people working at ETF in the world, mainly 90% 85,000 are in France. I'm also a member of the Sampling Laboratory, which is a mixed laboratory between ETF and Codépend in Paris, and CEREMA, which is the French navigation equipment bureau of the Environmental Ministry. And I will present to you the Telemac system. So before I start presenting you Telemac system, so Telemac is free, open source. So I will not try to convince you to buy it. So I will just to make you brighten your eyes, just to have in mind somewhere when we will begin your professional life, to remember that there exists a free code, an open source code, which is, I hope that I will convince you at the end that it is one of the best systems that handles, let's say, a wide range of high environmental problems that you can find in your real life. So you can start by playing it and build your own small model of your village or your small town to see if your house will be flooded in the next storm. But I think that I hope that you will use it in your professional life when you will handle much more complex situations. So what is Telemac? So Telemac is an open source, as I said, system of code. So it is developed since 1987. We will see later, but since 2010, it is developed in a consortium with 6 members, mainly, but there's a lot of contributors outside of the consortium. So there's three French partners, 2 British and one German partner. And as I said, there's a lot of universities that contribute. There's even freelance companies that contribute to Telemac. We will see that maybe if we have time. So. Okay, so Telemac, as I said, is a system of code. So to handle the real cases in the hydraulic world, so we need a lot of things. So first we need to simulate or to model the water. So the hydrodynamics, this is the main component of any hydraulic system. And for Telemac, we can handle the hydrodynamics. So we can see what we have the column here, the 1D, 2D, and 3D component of the system. So it is your choice to choose which dimension you need to use to simulate your case. Okay, so you will be the expert, and you will see if you see that you have really 1D behaving of your hydraulics, you will choose the 1D components. If you need the 2D aspects of behavior or the 3D, we will see that we can have the choice to use them, but also that it is possible to use them. So, because we have in mind before that the 3D, for example, or 2D large models are really expensive, and you see that with Telemac, one of the major benefits of this code is that it's one of the fastest in the world. Okay, with the parallel aspects and with the optimizing development of the code. So, if you are interested in real world applications, so as I said, you have hydrodynamics to reproduce, but also you can manage sediments. So you need to use morphodynamic components. You can manage waves. If if you are in presence of non-negligible effects of waves, for example, for storm surge, as Natalie said later. You need to manage also some water quality aspects, and in extreme cases, if you need to make interaction, for example, with underground water, you can handle these aspects using a dedicated component of the system. Okay, so this is the core component of the system, but to make, as you know, and as you have used it for your application in hydroeurope, you need pre-processing and post-processing tools, and with the delivery system also we provide some tools, but also in the community there's free and less free components to make the pre-processing and the post-processing. We give you some example, but there's not existed list. There's other tools that you can use. So I will start to give you some application, just to give an idea how we use. I will not present any equation. I will not present anything. I will just present you some application, just to have in mind what this code can do. Okay, for example, here, as you see, this is the Rhône River. It's the largest river in France in respect to the flow rates. It's not the longest one, because the longest one is the Loire River. But here, for the Rhône River, EDF has 4 nuclear power plants, active nuclear power plants, and we are interested to reproduce as Natalie has brilliantly presented the things, we are asked to respect the recommendation. Just to answer to your question, IRSN and ISN recommend to EDF to do things, and we have no choice than to follow these recommendations. So here, one example, when we see that we can have mixed 1D, 2D models for more than 300 kilometers on the Rhône rivers. So as you will see that models are getting bigger and bigger, and we are now speaking about landscape models, full river models, and we have no more, maybe in a couple of years, that no more war between hydrology and hydraulic in the field of modelizations. Okay, so this is the case of Rhône River. So the 1D component is the one we call Mascaré. So Mascaré is the 1D component of the Télémac Mascaré system, and there's for much technical aspects, we can do 3 kernels of computation, based mainly in finite difference and finite volumes. So I will not speak a lot about technical, advanced technical aspects. So I hope that somebody are using Mascaré, no? Or hydroeurope? No? Okay, first deception. Okay, so this is quickly one of the components. I will spend much more time to present the 2D component, which is called Télémac20, because I'm in charge of Télémac20. So I will say all the best about my baby, and I will present you much more applications about Télémac20. So Télémac20 is the oldest one. Okay? Old that not means that is out of date, but old that means in the simulation field. I hope that Olivier agreed with me that it has a lot of experience. So it's full. It has make evolution and followed all the standards of the software life. And as you can see that with AquaCloud, you can reproduce really all the complexity of hydraulics in the real world. Okay, so for numerical aspect, it is based on shallow water equations. It can be improved with one first order Bussiness equation to handle the dispersion effect. But the most important things are that it's based on unstructured meshes. So mesh of telemetry is triangles. It's not like other codes that are not cited here, but people are using mainly structured aspects, structured mesh, which for me it's one thing that is less flexible, let's say, to produce real geometries. Telemetry has two components based mainly on finite elements, but also finite volumes. And what you need in real world, you can find. So with tanks, dry zones, you can introduce turbulence models. You can handle pollutants. So if you have temperature or something which is polluted, maybe in water, you can handle with transport equation. You can handle oil spill, algae, water quality. If you have sources, all hydraulic structures, such as weirs, bridges, culverts, you can introduce them and use them in telemetry models. Okay. So, first application, for example, I can cite here is the tidal prediction and storm surge. So, storm surge, as Natalie said earlier, is what is produced by wind more than what is predicted by the tide. The tide is something which we can predict. Okay, it's just due to the gravity with the moon and the sun. So we can predict the tide and we can predict the height of water. Okay, but more than the tide, if we have a storm, we need to reproduce the water height due to these effects, and this is what we call the surge, or the storm surge. And one here, just a case, when I show you, this is the predictable tide, the component M2 of the tide, which is predictable. And this is the case that Natalie presented earlier also. This is the storm of 1999, when for our needs, for the safety of a nuclear power plant, we need to produce this case to predict, or at least afterward, to reproduce the storm that happened at that time, in 1999. Okay? Another application, and which is really crucial also for nuclear safety. Hopefully for French coasts, we are far from this let's say hazard, which is the tsunami hazard. But as you have seen, for Japan, for example, it's really important to predict the tsunami effects. And we were asked through some French project and European project, to be able to reproduce such kind of events. So the first case I will show you is this one tsunami. So it's a tsunami that happened mainly, we are not really sure, but it happens in 1755 in after a big earthquake that happened in the coast of the Portuguese coast in front of Lisbon. And we found, or somebody found, that in some newspapers that there's a small wave that arrived into La Rochelle and in the Irish coast also. So they thought that maybe it was a tsunami that happened just after the Lisbon earthquake. So by some assumption, we reproduce this case. So, and with the map, and we can see that here the propagation of the tsunami, and it's arrived to the French coast and the Irish coast, and we have probable observation data. We have and we retrieve at least the order of the range of the water rate. Okay, so the most important thing, I think, is to reproduce something which can be validated. So I show you here the case that theoretical, let's say, tsunami that we can reproduce in the laboratory. Sorry. So a solitary wave coming from the western part of the model and will arrive on an island, conical island, and a triangular shape, and we can see that the complexity of the case is really important to reproduce. We have the wet and dry effect, we have strong gradient of the waves, and we can reproduce it with telemap. I show you here a zoom of this case, and as you can see here, what we can see these nice edges, which are really important for real applications, where we show you a real case that these small edges explains lots of trouble that we have found for our application at ETF. So the code has to reproduce the details the model has been in, and this really not let's say, okay, presentation is going okay. Here the case that Natalie also evoked earlier. So this is the event of 1999, but I don't know why my movies are stopping. But okay, I will explain and then I will reproduce the movie. So what is really complex in this application? So the case of 99 of the Laie nuclear power plant is that the nuclear power plant that you can see in this photo is located at the estuary of the Gironde. So we have the effect of the river hydrodynamics, but also we have the effects of the Atlantic Ocean, which is not far from the nuclear power plant. So the hydrodynamics here is really complex. So we need to take into account river kind of hydrodynamics which is typical for rivers, but also we introduce the tidal effects, the wave effects, and all these the code needs to handle them in order to produce real results or trustful results, as you can see in the right of this slide. So the simulation results are compared with the observation. Okay. I'm sorry. My video is not working. Let's switch off here. No. Maybe there's some inertia. Well, he decided to show you the Japanese tsunami is getting crazy. I'm sorry. So I will try to speak in the same time that the slide is going by himself and not touching them. Okay? So here another typical application of Telemark, which is really important for you. So if you want to play with Telemark to reproduce the flattened map of your village or your town, you can use Telemark to reproduce the extent of urban flooding. So here I give the case of the town which is located in the northwestern part of France, which is Saint-Malo. And the upper border of the mesh is the Channel Sea. And this application showed that gave the flooding map of this town when there's a storm that induces waves that will overstop the protection dikes on the upper part of the model. Okay. I have an animation. I'm not sure that. So it's a freezing. So as you can see the wave coming from the upper part of the boundary and flooding the large area of the Saint-Malo buildings. So if you can see, the mesh is really adapted to reproduce buildings, roads, and all that you can find in the town. So if you have maybe with polytechnics, they are really experts in such kind of application with Morgan and Oliviers. So another case of urban flooding. So it's a case that we have done within the Tandem project, and it is a laboratory case. It's not a real town here, but it's a town that actually produced in the laboratory. And the case gives you a selected wave that came from the ocean and flooded the hypothetical town here. Another application which is really new, fresh, that just obtained these results maybe a couple of weeks ago. So it's the Valley of Kings in Egypt, which is really a nice application. It's not me, but some colleagues from Japan that worked on that. And if you can see, there's no water in this model. So in Egypt, it's really a desert. So you have just the Nile River, which is at the extreme part of the photo, and all the other model is really dry and really dry. So it's hot and dry, so no humidity, no water, no nothing. And they wanted to produce a rainfall event that happened maybe a couple of years ago, and that flooded the Valley of Kings. So there's some towns here that's from Pharaoh area, and they reproduced them. So this is the towns that where you can find the area of interest of this model. But, I'm not sure that I will try to show you the. So, as you can see, initially the lake is completely dry, and we make it, introduce the rain. It's a 50 years return period rain, and you can see that the resolution of the screen is not very well, but you can see that we can reproduce the runoff effects and the terms. We can reproduce the head that was observed 3 years ago or 5 years ago in the major event that happened on this model. So we have made the same thing for the River a couple of years ago. So I'm asking the question: is there anybody who is using Telemark for the River? I see a hand. Oh, that's I'm happy. 1, 2, 3. Okay. No, it was last year. Yeah. Okay. Sorry. Okay, this is another case that I'm showing you. It's a real nuclear power plant that is located on the Rhone River, which is called Curias nuclear power plant. And it's a local model. That means that it's not large model, physically large model, but it's just local model, because we use this model to explain what happened in Curias nuclear power plant. So several years ago, we observed that there's some algae, some plant vegetation coming from the river, and was clogged at the entrance of the nuclear power plant, and nuclear safety administration asked EDF to explain what happens with that nuclear power plant and why this event happened. And we built this model, and as you can see, when we make the simulation with Telemark, so here are the photos of the event. So you see that there's a lot of vegetation at the entry of the nuclear power plant. And when we reproduce the case, the hydrodynamics with Telemark shows that you can see that we see a recirculation structure, which is happening in the entrance of the channel, and it makes the entry of the channel narrow, more narrow than it was designed for. And this is what can explain why, if you have some vegetation or some algae coming from in the Rhone River, it will be cut in this recirculation and will not be able to leave. So it will be staying there, and it will make all the trouble or the issues that we observed, I think, in 2010, I'm not sure, but a couple of years ago. Okay? So another typical application for Telemark is application with ongoing importance. I think is the submarine turbines. So as you can see here, EDF started to install some submarine turbines in the northwestern part of France, near a site which is called Antipolis. And as you can see, we can reproduce the tide effect, and we can reproduce also the location of the turbines, as you can see in this rectangle. Okay? So here is the 3D view of this, the same site with the tide effect and the wet and dry effect near each de base. Okay, another typical application, as also by Nathalie earlier, is the dam break application. And one of the most severe applications for dam break, and hopefully we have data for that, hopefully we have data, but unfortunately the case happened in France, is the Malpassi dam break. Vous avez fait la visite? No? You know this event? So it's really a couple of kilometers from here. And it's not EDF property, that is important, I have to see it. So this dam broke in 1959 and caused hundreds of casualties. But what is interesting here is when we have all the observation at that time. So we have the water level, the wave arrival time, and also in the end of the 60s at EDF, we produced a really physical model of this case, and we have also lots of data about this case. And wait, I said it. So I will show you the animation. So initially the dam is located there, and at equal to 0, we assume that there's no dam, and the wave will arrive until the Mediterranean Sea. So the town of Regis is somewhere before the large part. This is another case also of flooding effect of nuclear power plant of Bankia on the Loire River. So I will go quickly. This is the last case of nuclear power plant of the nuclear power plant of Bugey on the Rhône River, but also it is impacted by the Seine River. So before, and this case, if the animation is really heavy, so my laptop is suffering. Okay. So as you can see here, we will produce a dam break of one of the biggest dams of France, which is called the Vauban Dam, and just to reduce the flooding effect of the nuclear power plant, which is, as you say, in the Rhône River. Another just typical application also to produce bridges on the dike. So as you can see here, also the Rhône River, and to show that we can reproduce the bridging effect. So this simulation is really old. It's maybe more than 15 years ago. Now with Tilman we can reproduce something which is much more heavy, much more realistic. Just a schematic case to reproduce, to show that we can reproduce the bridging effect and wetting and then the drying effect after the flooding period. Okay? The second major part of the system is that we have a 3D component in the Telemat system. 3D for you is maybe very complex, very heavy. Okay? So what is good here is that the 3D model is absolutely free. What does it mean in a computational point of view? It's absolutely free in engineering time, because if you have your 2D model, you can just add several keywords in your steering file, and you will obtain your 3D. There's no need to any additional pre-processing effect. Okay? Why? Because the 3D model, the mesh of the model is reproduced automatically by Telemac by extruding the 2D model. Okay, so I give you here a case. For example, here a river with two bridge piers. Okay, and you can see that the first effort to do for the engineer is to produce the 2D mesh. And just to say to Telemac, I need to produce 6 planes in the vertical direction, and Telemac will generate for you this space. The most important thing, which is computational and which you cannot find in the other codes, that it will change also the calculation kernel. So we will no more deal with shallow water equations, are 2D average equation. We will deal here with Navier-Stokes equation. Real free surface. It's not what we call a rigid proof assumption. It's a real free surface with real hydrostatic assumption. This is really important, really key points for a good 3D code that handles free surface flows. So I will show you some applications. So here is the option to how to reproduce the planes. I will squeeze it rapidly. So here some application when you need absolutely to reproduce the 3D effect. With a 2D code, you cannot reproduce such kind of effects. So the first case that you can find validation document of Telemac is what we call the log exchange. So imagine that you have hot water in the left and cold water in the right, separated by a membrane, or you can have something salty water in the left and fresh water in the right. And you separate them by the membrane, and at t equal to 0, you said, I have no separation, and I want to see how it will evolve in time. And you can see here the evolution in time of such application. Okay? So maybe you will ask it in your future work to reproduce the 3D model when you are sure that 3D effects are not negligible, okay? But you say that I'm building a long and large 2D model, and I'm not interested by the all 3D models. So I want just to see locally in some kilometers, several kilometers, the 3D effects. So what you can see just to reproduce the 3D effects in locally, so you can pick up a small part of the 2D mesh and you can build your 3D model local to optimize your computational efforts. Okay? I will give you, if my laptop allows it, several applications. So the first one is always the same nuclear power plant of Daniel, presented by Natalie earlier also. And we want to see the effect of rejecting hot water in the estuary of comment ça s'appelle? La Garonne? No? La Gironde, yes. Okay, so you can see here that we have 3 parts or rejection of hot water in the river, and we want to see the evolution of the temperature in the hydrodynamics. And you can see here we use the 2D mesh, but not all the 2D mesh. We just pick a box close to the nuclear power plant, and we reproduce the 3D model that you can see upstairs. Yes, and you can see here the evolution of the water with the tide going up and down, but you can see in the column you have the temperature evolution. So, okay, change to another case in 3D that you can I can show you. It's what was built by our colleagues in Canada. So it reproduces the tide effects on the Fundy Bay in Canada, and it's the location in the world where the tide effect is the most important. This is really important. So we can have more than 15 meters of variation, plus and minus 15 meters in these locations. So it was achieved here, accelerated animation. It was achieved by Technic 3D to show you. It's really a huge, in 2D, it's a huge model. Okay? Okay. This is the case I showed you earlier with this one tsunami that you can handle using 2D or Pushkinas or 3D models, and it is your choice to, as expert, to choose which model you want to use, but you have to assume the responsibility because the different models means different results, and you have to assume later that these differences you will be able to explain why these results are different. Okay. The last case is the Belle Lagoon. Belle Lagoon is a lagoon which is located just close to Marseille in the south of France, and it is connected with the Mediterranean Sea. As you see, the red part is the Mediterranean Sea, so red means salty water, and blue means fresh water. Why we are interested in that case? Because EDF has a series of hydroelectricity power plants, and they end in the blue part that you can see at the upper part of the, which is called the Saint-Chamond power plant. And we are asked to guarantee that the hydrodynamic of the Belle Lagoon and the water quality also later are not affected with these fresh water will be injected in the Belle Lagoon. Okay, so as you can see, this is a 3D model. Yes. Okay. And you can see in the bottom of the model, this is the lower view of the model, that you can see salty water which are introduced in the lagoon. Okay, as I said, for 2D and 3D compounds, we can produce oil spill, algae, and here an application of, for example, application in Morocco that we call the Brusnica Bay, and we want to retrieve. If you suppose that we have a lake which is polluted by something, the authorities wanted to say or to know after how many tidal cycle the water in the lake will be renewed. So as you can see that at t equal to 0, the lake was polluted entirely, and we have reduced a lot of tidal cycle. And we see that the water in the lake is being renewed and getting cleaner, let's say. Okay, I will skip all the other parts, let's say, just to show that we have models that handle the waves in local models, but also in really large models. So it's called, which is called Artemis for local model, and the other code which is called Tomahawk that handles wave in very large volumes. So this is Tomahawk. So you can see that we reproduce the waves in the northeastern part of the Atlantic Ocean. We have the morphodynamic component for the dynamic system also. We can simulate here, for example, the dredging effect, the dilution of the dredged mass. Here, also the same case of the Blaine. And this is a real case of evolution of the morphodynamics. These simulations are also very old. I think it goes back to 2005. Just to give you an idea about the capability of the code, that look at this simulation. This is the simulation evolution after 1 year, one physical year. Okay, so the same case was achieved for 10 years also, using 8 processors. So what you can have in your laptop, this case can be handled with your laptop, and I'll give you here the zoom on that, but for the simulation of 10 years, and you can see that the evolution of the perfidency from 1995 to 2005, with a computation that stayed 2 days of computation on 2 processors in 2005. Okay, now this simulation, if we reproduce it, it can be in 30 minutes. Okay, so this really major point that you have to keep in mind, that the parallelization capability of Telemac are helping a lot the engineering community to handle much more bigger models and with much more complexity to produce real cases. This is another application of sediment replenishment on Japanese. I will skip all this. So as I said, the parallelism is really important. So just to give you some ideas, the scalability, which means the maximum CPU that you have used, goes up to 18,000 CPU for the Malpassé test case in 3D, with a mesh that is of about 200 million nodes. It's really huge meshes, and these are really important for the industrial code. So I will skip also the uncertainty quantification, because Nathalie gave you an exhaustive overview of that. So the water quality also, I will skip it. One thing which is really important for you also is you can couple all these or major part of these codes to introduce more and more complexity if you want to handle in the same time, for example, waves, sediment, hydrodynamics, and water quality. You can couple 3 or 4 codes in the same time to make your simulation. This is really a big advantage of the Telemac system. As I showed you on the first slides, also you can couple 1G, 2G, or 2G, 3G codes using a common platform, as if you want to play with the coupled code also. So you have all the possibility to reproduce real cases in environmental applications. The development I will skip. Just the last word. If he wants that to be skipped this slide, so okay. So this is very important that we give the code and we give also assistance. And you can find everything on the website of Telemat. So you can find documentation, you can download the code, you can download the validation cases to introduce or to start with the code also. And you can find all the problems or the issue that you can find when you start with the code, and we have a forum that can give you all the answers about the question that you can need with your code of Telemat. So, as I said you earlier, I'm in charge of the 2D code, so you can find me, and I will answer to your questions. So there's a whole team behind every component of the code, and we try to do our best to answer within 48 hours to your questions. Okay? So while Philip is coming, so I will this is the sign that I have to start to stop. No, I'm just yes. Is there any question, Mr. Chairman? Yes, please question.
Is there any is it easy to communicate policy between the
Just a question about how to collect data for water quality. Which data you need to model water quality in telecom?
This is two. This is two. This is two questions. No problem. The data for water. The data for water quality you can obtain. It's not my scope of it's not my skills, but if you want to use Telemat for water quality, it's your task to collect data. As it's your task also to collect bathymetry, to collect the hydrology of your model. If you are interested in water quality, it's your task to collect it. If you want to reproduce temperature, for example, or pollutant, any pollutant of your lake, for example, it's your task to retrieve. Is there some measurements or some body of work interested before to collect these data?
something like biological
Yes.
engineering, something like that?
Yes. You can. It's the matter of people who are collecting this data. So if you can with Telemat produce temperature, you can produce biological processes. For example, if you have any kinetic bacteria, anything, you can reproduce the spreading in the water. But it's your task to retrieve the measurement, to make the calibration, to make, if you have some prediction to do, you use Telemat to do it. Any other question? I think you are hungry, that's it, or tired. for your.
Salido directo con YouTube.